All right, as we can continue on, let's look at this picture. So on the right, you have a picture of the Earth, and this is to represent the Earth as it is, the universe as it is. If we believe in a higher being, this is what God created. This is our Earth as it is right now. And it's important to understand that science is not the same thing as the Earth. It is not the universe. Science's job is to describe our world, to describe our universe. And it's important that in science we need to understand that we want to get as close as we possibly can to the way the world actually is. So our descriptions, we want them to get better and better. We want our models to get closer and closer to what is actually occurring in the world. And so it's important that what we do in science is we make a model, we make a description, and then what we do is we find the parts of it that don't work, the parts that are bad, and then we can make it better. And hopefully we're getting closer, and we're getting closer, and we're getting ever so much closer to the way the world actually works, to the fact that what we are describing in science is as close as possible to the way the world actually is. But here's the thing. These two can never be the same theoretically. If I ever say that I have arrived over here and that my science is a perfect description of nature, and it's a perfect model that can never be disproven, never is false in any situation, under any circumstances, then science has ceased to exist, at least in that realm, at least in that arena. So it's important that we understand that in science, all we do is we make our descriptions and our knowledge better and better and better. We're just getting closer. In our descriptions, we're trying to get closer and closer to the way the world actually is, to the way it actually works. In order to do that, we do research. There's two specific types of scientific research that we do. One is called qualitative or descriptive research, and the other one is quantitative or experimental research. Qualitative and quantitative. Hopefully you understand the roots of those words. Qualitative, the root word is quality. When you think about someone's qualities, you're probably not going to use numbers to describe them. A qualitative research is done when experimentation is either useless or impossible. We use numbers sometimes with qualitative research, but it's not necessary. For instance, a qualitative research example would be if someone is trying to describe a new species or to describe a new planet or celestial body that they found. That's qualitative research. All we're doing is describing something. We can use numbers. We can always use words like, it's cold there, it's warm there, this new snake is green. We can use words to describe things. That's qualitative research. But then there's a different type of research, and this is the one that is probably more common and the one that's a little more useful to us in terms of scientists, and one that we tend to delve into a little more often is quantitative research or experimental research. Experimental research is used for either more detailed descriptions. So I want to know, now I've described this new species, now I'm going to dive into it further and talk about how it works. How are its lungs different from another species' lungs? For that, I need experiments to really understand that species. I'm also going to test hypotheses. If something's going on and I want to explain why that is, I'm first going to form a hypothesis, then I'm going to test that hypothesis using an experiment. For experiments, quantitative research, numbers are almost always used because we have to be able to quantify the effects that we see. An example would be answering this question: how do insecticides or herbicides affect amphibian populations? It's a very good question. I can't answer that using qualitative research. I can't just go out and look at stuff and go, oh yeah, it's affecting the amphibians poorly. We have to do very specific experiments to determine the answer to this question. All right, and that leads us into, along with quantitative research, we need to understand when we're using numbers, we have to measure things. So we need to talk about measurements. You have a map on the screen. There's a lot of green countries and there's a few gray ones. And this map is off of Wikipedia. And the title of it, there's a gray one right here. The title of this map is Countries That Use the Metric System. So there's always a joke that the whole world uses the metric system, except for the United States and a few other extremely undeveloped nations. The United States is one of the only undeveloped or the only developed nation that does not use the metric system in an official capacity. So we're going to talk a little bit about the metric system. If you don't know what it is, the metric system is very simple. Here's some videos that you can go watch. I'll put the links in the description of the video, but we watch those in class. The metric system is simply a system of measuring based on units of 10, which makes it really, really easy. All we have to do is move the decimal. It's not like the customary system like we use in the United States with gallons and cups and pints, where we have all these goofy measurement conversion factors that we have to use. We don't have that in the metric system. Everything is a unit, is a 10-based system. Why do we use it? Well, basically, what happens in science is that if we do an experiment here in the United States to test a hypothesis, that experiment has to be repeated in order for that hypothesis to become a theory. And so what we do is we put the results of our experiment out for the scientific community at large for them to analyze it. But in order for them to analyze it, they have to understand the measurements that we took in our experiments. In other words, if we take weight measurements in our experiment in ounces and pounds, nobody else in any of the rest of the world uses those measurement units. And so they're probably not going to understand what is written in that paper. So we have to standardize all of our measurements. So whatever we do in science, if I'm measuring weight, I have to use newtons. If I'm measuring mass, I have to use kilograms. If I'm measuring length, I have to use meters or centimeters or millimeters or something like that. This is the SI system, the international system. SI is System International. It's a French word. That's why we use SI. But it's an international system to ease communication across the scientific community so that we understand the measurements that we're taking across the world. Didn't mean for that to happen. If I told you to name some metric units that you know of, it might be hard for you to come up with them. And the reason is because here in the United States, we don't really see the metric system very often in the US. Chances are, if you are familiar with a unit, for instance, people usually say miles. Well, we're very familiar with miles. You know how long a mile is. You understand what it means if you're going 60 miles an hour. Chances are, if you're familiar with that unit, it is a customary unit or a standard unit. It is not metric. Again, because we do not use the metric system by and large in the United States. The only place that we do use the metric system is in some of these things like this. Any food measurements, soft drink volume rather, nutrition facts, camera lenses, most common camera lens size is a 30mm lens, you might see that there. Olympic sports, all of these things are international. And that's where, as the United States, as a nation, we are forced to use the metric system, because we want to do well and compete in those things. And so we do use the metric system for anything that's international. But if you think about anything that is uniquely American, like baseball or football, we don't use the metric system. We use yards, we use feet. That's customary, not metric. So basically, if there's any unit that you're very familiar with, it's probably not metric. And we're going to talk about some common metrics as we go along. For us in physics, we're going to measure length in meters. We're going to measure mass in kilograms. I mentioned that before. Time is in seconds. That's pretty familiar to you. But temperature, we're going to use Kelvin and Celsius instead of Fahrenheit, and lots of other examples of units that we'll use. So this is our short brief on the metric system. To our discussion of quantitative research. When we do quantitative research, we have to go through a process. We have to use a specific method. You've heard the scientific method for a long time now, and I'm sure you understand that there's several steps. You also need to understand that those steps aren't always followed in a sequential pattern. But I do want you to understand that there's certain terms that are very commonly misunderstood that you need to know the definition of. First of all, a hypothesis. A hypothesis is very simply kind of like an educated guess. It's an educated, and it's very important that we know, it is untested. It's an educated, untested explanation of an observed phenomenon. It is to be tested. We are going to test a hypothesis. That's the purpose of a hypothesis. It's not to give a reason, it's to give a possible explanation so that we can understand how to proceed and test that possible explanation. You need to understand that this is the way we work in daily life, in everyday life. I gave the example earlier of you wake up in the morning and your car doesn't start. The very first thing you're going to do if you're going to try to solve the problem, now you could just take it to a mechanic, that's not science. But if you're going to do science and try to solve the problem, the first thing you have to do is come up with a hypothesis. Even if you don't state it in words, you're thinking it. Your first hypothesis might be, I don't have any gas. And you might look at your gas gauge to see what it shows. Your gas gauge shows full. That means your hypothesis was not correct, and you trash it. And you go on to another hypothesis. Maybe my battery is disconnected. You would open the hood and you would check your battery connections. If they're good, you trash that hypothesis and you move on to another one. Maybe my battery is dead. That's another hypothesis. You can test that with a voltmeter. You measure the voltage of your battery, it's 12.5 volts. You have a good battery. You trash the hypothesis. You understand what I'm saying? We make hypotheses to test them, and then we either trash them, or we might modify them or support them completely. A supported hypothesis is the only thing that can lead to the next step. And the next step, after a long, long time, is a theory. It's really important that we understand what theory means. So a hypothesis is to be tested. A theory has been tested, which is a big difference from the way that the world uses the word theory. People might say, well, I have a theory about that. Well, what they really mean is they have a hypothesis about that. Usually when people say that they have a theory, it's a guess, it's an educated, untested explanation of some sort of phenomenon that they've observed. They probably haven't tested it. Now, if they really tested it, they probably are a scientist, in which case it's a theory. But most of the time, that's not the case. So a theory is tested. And being tested, it has been well substantiated. It's a well substantiated explanation of an observed phenomenon. So both of these attempt to explain a phenomenon, but a hypothesis has not been tested. A theory is the result of multiple times that a hypothesis has been supported. It's a well substantiated explanation of a hypothesis. We're going to accept that that's relative fact. It's the result of a repeated experimentation. Now let me caution you here. It's still not fact. We still can't prove anything. We can still improve this theory as well. But it's important to understand that theories have been tested. They've been well substantiated. And then we get to a law. Important difference between a theory and a law. A law is a description of an observed universal phenomenon. For instance, the theory of gravity, the law of universal gravity rather. Newton's laws of motion we're going to study. The laws of thermodynamics. Coulomb's law explains electrostatic force and static electricity. All of those things describe an observed phenomenon that happens everywhere. Everywhere we can see. Or at least almost universal. It's important to understand this. Laws do not explain why the phenomenon exists. That is more the job of a theory to explain why that goes on. And it's important to understand sometimes there are no answers. Why does gravity exist? That's a huge question. Why, in terms of Newton's laws, why does an object keep moving when it was in motion? That's a big question that isn't answered by Newton's laws. Newton's laws just describe the universal phenomenon so that we can move forward. Very important that you understand the difference among a hypothesis, a theory, and a law. You need to know those terms. Lastly, very quickly, we need to understand the difference between science and technology. Those two, the lines get blurred between the two. What's the difference between them? Well, basically, technology is the application of science. It's an applied science. So what we're going to do is take the knowledge we've gained in science and we're going to apply it to things that make our lives better. So science is gaining knowledge about the world that we live in, about the universe that we live in. Technology is taking that knowledge and using it to create things that make our lives better. So in your notes it says, what things has science given us? Well, science basically gives us the things that we know about the world. We know the world is round. We know that there's 21% oxygen in our atmosphere. We know that our planet revolves around the sun. We know that positive is attracted to negative, and negative and positive repel, and positive repel. All of those things are science. Those are things that science has given us, knowledge. Technology uses that knowledge to give us things like cell phones, TVs, electronic devices, not only electronic devices, but mechanical devices as well, cars, windmills, all kinds of things. These are mainly going to be devices that use scientific laws to run and to make our lives easier. So we need to understand the difference between science and technology. And that's it.